Many people hate physics, but I believe everyone would love physics if it's taught in a right way. I have learned how to teach physics in a deep yet easy understanding way after tutoring thousands of students for more than a decade. If you ever feel you get stuck, go ahead and ask me a question, and I personally answer every and each of your questions. I can make learning physics sweet and enjoyable for you. My name is Mohammad, and I'll be your wise instructor for physics. Displacement, velocity, and acceleration could be connected to each other using kinematic equations. We can use this type of equations to find missing information for any kinematic problem. We have a different set of equations depending on type of the motion we're talking about. Here we learn how we can find kinematic equations for constant velocity motion and also constant acceleration motion. First, I'm going to introduce the motion with a constant velocity. If I have a constant velocity in the motion, so then we have one single equation which relates kinematic quantities together. That's given to you in the box. We have x minus x naught equal to v multiplied by time. So here, x minus x naught is basically displacement of the object, displacement. V is the speed or the velocity of the object, and t is the time it takes to complete this motion. You can consider that x naught and x here are the initial and final position of the particle. That's why if we subtract final position by initial position, we can find displacement of the object during that time. We can also have the set of the equations when we have a constant acceleration motion. If you have a constant acceleration, now velocity is changing. That's why we can talk about initial or final velocity of the object during this motion. We have three useful equations which are shown here in the boxes. Let me go through each of them one by one and introduce them to you one by one. The first equation is x minus x naught equal to half of a times t squared plus initial velocity multiplied by time. As you can see here, still we have x minus x naught, which is final position, minus initial position. And similar to the previous motion, we have basically displacement of the particle during this time. Here, a would be acceleration, t is the time it takes to complete this motion, and v naught or v0 is the initial velocity of the object at which it starts the motion. If you notice, this equation is very similar to what we introduced earlier for the constant velocity motion. For the constant velocity, we just had x minus x naught equal to vt, but here we have one extra term, which is 1/2 of at squared. Basically, these two equations are exactly the same. When we have a constant velocity motion, in that case, acceleration is simply equal to 0 because velocity doesn't change. And if I set acceleration equal to 0 in the second equation, we can find the first equation introduced above. So technically, we're talking about the same equation. The next equation we have for the constant acceleration motion is what we have on the second box. We have v equal to v initial plus a times t. So here, v is the final velocity after time t, and v0 is the initial velocity, and a would be again acceleration. I can rearrange this term and write it down in a slightly different form. I can write it down as a equal to v minus v naught divided by t. And here v minus v naught is basically the difference in the velocity during the motion, which is delta v. And we can recognize that delta v over t is basic definition we had for the acceleration. Finally, the last equation I want to introduce here would be vf squared equal to v initial squared plus 2 times a times x minus x naught. This is a very useful equation because, as you notice, there is no time dependence there. And we can relate final velocity, initial velocity, acceleration, and displacement. So here, as I mentioned, vf would be the final velocity, v naught would be initial velocity, and x minus x naught is basically displacement of the object. Notice that depending on the question given to us, we are able to pick any of these three equations to find for the unknowns. But we want to make sure that we only have one unknown in the equation. Otherwise, we cannot solve the problem. I want to just emphasize again that kinematic equations introduced here are only useful when we have a constant acceleration or constant velocity motion. If we have a more complicated motion in which, for example, acceleration is changing as well, then we cannot use the set of the equation introduced here. We need to have more complicated equations which are basically beyond the scope of this course. Next point is that in order to find the right equation to pick, the best strategy would be to list all the known and unknowns given to us in the question, and then we can pick the equation for which we have only one unknown left. In addition, it's very important to pick the right sign for velocity, acceleration, and displacement when you insert numbers in these equations. Remember that velocity, acceleration, and displacement, they are all vectors, and vectors have direction as well. Since we are talking about a one-dimensional motion, we can represent these vectors with positive and negative signs. It means that when you want to insert the numbers for velocity, acceleration, and displacement to the above equations, we need to consider the right sign. Otherwise, we get the wrong answer. Now let's summarize all the steps we need to take to solve any kinematic problem. The first step would be to draw and label a nice diagram. In most physics problems, having a schematic picture of what's happening helps you a lot to guess what should be the next step in order to solve the problem. Next step would be to define a coordinate system. It means that we need to decide which direction I want to consider as x direction, which direction as y direction, and what is the positive direction of x and y axis. Notice that you have a freedom to choose any direction as x and y, and any direction as a positive direction of those axes. However, you need to be consistent in using this coordinate system and positive directions. So at the end of the day, if you remain consistent, you should get the same answer no matter which coordinate system you picked. In the next step, we're going to identify all the known information or all the known variables given to us with the appropriate unit in front of them. Then we're going to pick an equation which is basically relate all the known information we have with the unknown asked in the problem. Notice that if we know any three of these quantities, delta x, which is displacement, initial velocity, which is v naught, final velocity, which is vf, acceleration, and time, we should be able to find all the other ones based on the above equations. And then in the next step, now we are ready to solve for the quantity we are looking for. We basically pick the right equation, insert all the known information, and find the unknown. But just be careful because you want to make sure that you insert the numbers with the right sign. And finally, at the end of the day, make sure you think about the final answer, especially check the sign of the final answer and see if it makes sense physically or not. For example, if we see that eventually the particle is moving upward, it means that we expect velocity to be positive if we define upward velocity to be positive. So if you end up to get a negative number for velocity, it means that you've made a mistake somewhere. You can get back and fix the problem. So it's very important to think about the physical meaning of the final answer you get. In this example, we're talking about the stopping distance of a driving car. Let's read the question together. A car can decelerate at 4 meters per second squared. If somebody is driving this car at 110 kilometers per hour and human reaction time is 0.45 seconds, what will be the stopping distance for this driver? Okay, so let's see what does it mean here. So we have a car which is driving. Let me have a schematic picture for you. We have a car which is driving here, and the speed is 110 kilometers per hour. So imagine, for example, the driver sees a kid, jumps in front of the car, and he wants to stop the car. Based on the information given to us, we need 0.45 seconds reaction time. So from the moment it sees the kid till the moment it pushes the brake, there's a 0.45 seconds. During this time, the car is going to move forward at a constant speed of 110 kilometers per hour. So we know that the time for this section is 0.45 seconds. At the end of this path, still the car is moving at 110 kilometers per hour. Now the driver pushes the brake. What happens? We have a decelerating motion, which means that we have a slowing down motion. So in the second phase of this motion, eventually the car stops. So now finally at the end of the path here, the car gets to the final velocity of 0. And from this moment here to the final position, we have a decelerating motion with A equal to 4 meters per second squared. But be careful, because we know that acceleration is a vector and vectors have directions. Since we're talking about a one-dimensional motion, we can show direction of vectors by signs. So here, because we have a decelerating motion and the object is moving forward, we expect acceleration to be opposite to velocity, which is pointing backward. As a result, I need to have a negative sign for acceleration. So I consider A to be negative 4 meters per second squared, because we have a slowing down motion. Okay, in the second part, we just know the initial velocity. Let me show it by V0, which is 110 kilometers per hour. And we know the final velocity, which is 0, because eventually the car stops. But I don't know how long it takes for the second part. But notice that in the question you're asked to find what's the stopping distance. I need to know how much is the distance traveled in the reaction time period and how much is the distance traveled in the next phase, and then add them together. That all together gives you the stopping distance for the whole motion. Okay, let me call the distance traveled in the reaction time to be d1 and the distance traveled in the second phase to be d2. I'm going to calculate each of them one by one. Let's start with d1. First, we have to recognize what type of the motion we have here, because we have a different kinematic equations depending on type of the motion. In the first part, in the reaction time period, we know that the car still is moving at a constant speed of 110 kilometers per hour. There is no change in the speed. As a result, we have a motion with a constant velocity. For the motion with a constant velocity, we have only one single equation. X minus x naught equal to speed multiplied by time. So here, x minus x naught is basically the distance traveled by the car at this moment. So that's why we call it d1. And then v is the speed of the car during this motion, multiplied by time of this basically section, which is the time of the reaction, or the reaction time basically. But in order to find the distance in the right standard unit, I first need to convert the velocity given to us into meter per second. So here we have the speed to be 110 kilometers per hour. And in order to convert it to meter per second, I need to convert kilometers to meters and hours to second. So I'm going to consider each 100 kilometers to be 1,000 meters and each hour to be 3,600 seconds. So if I multiply 110 by 1,000 over 3,600, I can find velocity in meter per second. The number I have for this is equal to 30.6 meter per second. Okay, now we're ready to find the first distance. d1 would be equal to speed, which is 30.6, multiplied by reaction time, which was 0.45 seconds. So here the distance traveled for the first part is 13.8 meters. Now let's look at the second part of the motion. In the second part of the motion, we started with the 110 kilometers per hour, which we found to be equal to 30.6 meters per second. And eventually, we stop at the end of the path. So the final velocity would be 0. And we know that we have an acceleration equal to minus 4 meters per second squared. And I want to find distance. So let's think about all the known and unknowns. We know initial velocity, final velocity, acceleration. And we are looking for distance. Think about the list of the kinematic equation we have and pick the one which has only one unknown left there, which is the distance we're looking for. Well, you can easily notice that the most appropriate kinematic equation for this step would be v final squared minus v initial squared equal to 2a multiplied by x minus x naught. So here, x minus x naught is basically the distance traveled in the second part. Let me show it by d2. V final is basically the final velocity, which is 0 because it stops eventually. And we already know v initial and acceleration. So we are ready to find the distance here. Let me first solve for distance from this equation. So d2 would be equal to minus initial velocity to power 2 divided by 2 times a. But be careful, because when you insert numbers for the acceleration and velocity, we have to insert them with the right sign. So here, I already converted velocity of 110 kilometers per hour into meter per second, which is 30.6. So we have minus 30.6 to power 2. So since we have an object which is moving forward, we can define forward direction to be the positive direction. And since the direction of the motion is toward right, the velocity at any moment would be positive. That's why we have velocity here with a positive sign, plus 30.6. In addition, because we're talking about decelerating motion, we said that acceleration vector should be pointing opposite to velocity. So since velocity was forward, acceleration should be pointing backward. As a result, we have a negative sign for that. So we have 2 multiplied by deceleration, which is -4. The number I have for this distance is equal to 117 meters. Okay, so to find the total distance traveled during this stopping motion, total distance, I just need to add the 2 distances I found above. So the first distance in the reaction time was 13.8. The second distance was 117, and altogether I have 131 meters. That's the total distance traveled.
Want more bite-sized lessons? Check out the Wise free trial at wizeprep.com. Oh, and subscribe to our YouTube channel while you're here.